Hello everyone, and thank you for attending today's webinar, Testing 5G and GNSS Hybrid Positioning, presented by Spirent Communications and Fraunhofer IIS. I'm Romain Zimmerman, Business Development Manager for Spirent, and I'll be moderating this webinar. Our speakers today are Ivana Lukshin, Scientific Researcher at Fraunhofer IIS, and Steve Douglas, Head of 5G Strategy at Spirent. You can read their biographies on the right side of your window. Just a few technical notes before we begin. If you'd like to download the slide deck, please click the link in the resources list on the left of your screen. As an additional resource, at halftime, we'll be conducting a poll which we would like you to participate in. This webinar is being recorded and will be available on demand in a few weeks. We will follow the presentations with a Q&A session. Please submit your questions using the Questions and Answers tab on the right side of your screen. Okay, now let's begin. Steve, please go ahead.
Thank you, Roman. So let's first introduce 5G. It's the next generation of cellular communications, which is currently being deployed across the world today. And it aims to be a radical leap, which will transform communications with blazingly fast speeds, really low and ultra-reliable latency, and ubiquitous connectivity of everything. And at its heart is an ambition to become a general-purpose technology like electricity and the automobile, a technology simultaneously servicing consumers and industries alike. In essence, a critical enabler for all types of digital industries and services, including our transportation systems, our factories, our manufacturing plants, our healthcare systems, our cities, and even our security and defense industries. And our communication networks are evolving like never before to meet this potential, moving from a rigid proprietary hardware environment to embrace cloud-native architectures and virtualization, allowing the network to be disaggregated and distributed to the edge, creating new service delivery paradigms. We'll be harnessing the power of big data, AI, and automation to enable the networks to be dynamic and agile, flexibly and optimally servicing all types of consumers and industries. And if we stop and look at the 5G network, it's getting more and more complex across all domains to meet this goal. At the bottom of the architecture, our transport networks are evolving to support new speeds, protocols, and interfaces required for multi-service flexibility. This includes the move towards any-hall networking. Next, there is a dependency on network virtualization and software-defined networks to support the new 5G core, disaggregation, edge clouds, and the future virtualization of our radio. And in regard to radio, it is dramatically evolving to support new frequency ranges and new antenna technologies. Our core is evolving to become a cloud-native and service-based architecture designed to offer the service agility that only hyperscalers enjoy today. And if we look at the new device types, they're going well beyond smartphones and IoT devices into the world of connected everything, where new chipsets and antennas will harness the power of multiple radio frequencies to offer new experiences and location accuracy. And finally, there's a new breed of applications being enabled as 5G moves beyond traditional voice, data, and video services. These new applications require all of the underpinning domains and radio networks and frequencies to work in unison and provide specific capabilities to meet each use case need, whether it be ultra-reliable low latency, guaranteed high throughputs, enhanced location accuracy, or seamless mobility, to name a few. Now let's delve a bit deeper and look at the 5G new radio, which is a fundamental part of this evolution and critical to enhancing location accuracy. We're opening up new ranges of spectrum, from low bands beneath 1 GHz, which are ideal for low power and long range coverage for massive machine type communications, to mid bands between 1 and 7 GHz, which offer a good mixture of coverage and capacity and are ideal for enhanced broadband services and time-critical processes. Through the previously believed unusable high bands or millimeter wave ranges above 24 gigahertz, which are ideal for high-capacity, short-range, line-of-sight services and high-speed over-the-air networking. And from a positioning perspective, the 5G new radio opens up many new opportunities for enhanced accuracy. 5G as a wideband technology offers higher bandwidths, enabling more positioning information, such as positioning reference signals, to be exchanged between the device and the 5G base station. The use of massive MIMO and beamforming antenna technologies by 5G allows us to slice the radio base station transmissions into many spatial components, just a few degrees apart, providing far greater location accuracy. And 5G beamforming is a multidimensional technology supporting not only horizontal but vertical Z-axis positioning by identifying which vertical beam a user is occupying. And then you have the densification of our networks, with 5G outdoor and indoor small pico and femto cells deployed in close proximity to meet the challenges of RF propagation and to offer line-of-sight radio paths. Now, this creates a happy byproduct where location accuracy can be greatly improved. So what's driving the need for greater location accuracy? Well, there are three main drivers. Firstly, you have regulatory. The most influential is the regulatory requirements for mobile emergency calls, E911, set by the US Federal Communications Commissions, or FCC. Other entities piggyback on these requirements, such as the European Union's E112 and Automotive's eCall. The FCC has been driving increasing location accuracy for almost 2 decades, and their latest requirements call for indoor accuracy within 3 meters for 80% of all indoor 911 calls by 2021. Secondly, you have commercial drivers. Today's requirements for commercial positioning are coming from a long list of new and envisioned human-to-machine and machine-to-machine use cases. These include things like augmented reality, fitness wearables, asset tracking, connected autonomous vehicles, and many, many more. Here you have a diverse range of requirements for location accuracy, ranging from less than a meter to 30 meters, time to first fix from 1 to 30 seconds, and location availability from 80 to 99.9%, depending if the use case is mission critical or not. And thirdly, you have military. Today, our defense and security sector are exploring how they could benefit from the adoption of a commercial technology such as 5G, which is both cutting edge and highly flexible to help meet ever-evolving challenges of modern threats, including improved intelligence, surveillance, and reconnaissance systems, robust new methods for survivable command and control, and streamlined logistics for smart bases. So let's look at the main location techniques which are available during the first release of 5G, which is based on the 3GPP Release 15 standards. The first point to note is that 5G will still employ 4G LTE positioning technologies. You will have network-assisted GNSS, which makes use of user equipment that is equipped with GNSS radio receivers, and a continuously operating GNSS reference receiver network, the location management function, which is clear sky visibility of the same GNSS constellation as the user equipment. The location management function assists the UE with either sending data to assist the UE calculating the position or calculating the position itself and then sharing it to the UE. You also have observed time difference of arrival, which makes use of the measured timing of downlink signals received from multiple transmission points. Enhanced cell ID is another method where the position of the UE is estimated with the knowledge of its serving base station and cell. The information is obtained by paging, registration, or other network communication methods. There is also the support for the use of beacons, Wi-Fi, and Bluetooth, meaning the UE can measure these received signals and with the assistance of the positioning server calculate the location. Barometric pressure sensors can be used to determine the vertical component of the position of the UE. And finally, you have augmented GNSS with correction services using real-time kinematic state space representation and precise point positioning. These augmented capabilities offer higher degrees of precision to centimeter level, and they offer robustness. They rely on ground-based reference stations that use additional data from navigational satellites, plus advanced error correction algorithms to generate a much more accurate signal. They then transmit this signal to the receiver device. And the choice of implementation of these techniques is flexible, supporting hybrid positioning using multiples of them, or standalone modes without any network assistance. Then we move to Release 16 of the 3GPP 5G standards, where 5G new radio will now be used to enhance the current location methods and support new targets for accuracy and performance, including indoor accuracy of less than 3 meters for 80% of UEs. And there are a number of new methods which are now considered. Picking 3 examples from the new methods listed here, you have downlink time difference of arrival. Downlink time difference of arrival makes use of a new reference signal for the UE to perform downlink signal time difference measurements for each transmission point to help locate the UE in relation to the neighbouring transmission points. Another new method is uplink angle of arrival, which makes use of the measured azimuth and zenith of arrival at multiple reception points of uplink signals transmitted from the UE. The resulting measurements are used with other information to estimate the location of the UE. And then you have multi-cell round-trip time, where the base station and the UE perform receive and transmit time difference measurements for the signal of each cell. The measurement reports from the UE and the base station are sent to the location server to determine the round-trip time of each cell and derive the UE's position. These new methods, combined with current methods I've previously discussed, will create new, more accurate hybrid positioning capabilities to meet the requirements of regulatory, commercial, and military. And the ambition doesn't stop here. With Release 17, the goal is for even more accurate positioning, with targets of less than 0.2 meters for industrial IoT use cases. And to exceed current day performance and meet the evolving needs for more stringent accuracy and speed, many innovative technologies are also being developed and used. Advanced Wi-Fi technology introduces fine time measurement to measure the distance between an access point and a device within 1 to 2 meters accuracy. With multiple access point measurements, triangulation can be performed to get a very accurate location. Then there is terrestrial beacon systems, which I commented on earlier. These systems are now being used with indoor penetrating radio deployed on cell towers to create precision triangulation networks. And GNSS systems are evolving. The US GPS system introduced the L5 internationally protected frequency band to improve accuracy and signal robustness, including interference mitigation. And most smartphones today now support this, including multi-GNSS, where GPS plus another GNSS constellation is supported. To be clear, 5G new radio's role is an enhancement, but a critical enhancement for positioning accuracy. In a recent study done by 3GPP assessing positioning performance targets, it was clear that while existing positioning technologies can already cover a wide variety of demanding use cases, especially when they're combined, some very demanding and critical accuracy targets are not met, and this requires new positioning technologies such as 5G. This is particularly the case to fill the gaps of high accuracy for indoor, for deep urban environments, and for relative positioning in enhanced positioning coverage areas. Now, this is going to be critical to service industries such as transportation and autonomous vehicles, smart factories and robotics, mining, military theatres of engagement, and healthcare for areas such as patient monitoring. It's also clear that while 5G will certainly be needed to enhance today's positioning accuracy, it's only really one tool in our toolkit. And to deliver holistic and robust location accuracy, we will have to integrate a multitude of sensors and technologies into a hybrid positioning scheme. And if we look at the timeline for positioning technologies to incorporate 5G enhancements, this will occur in phases over several years. In the first phase, with the first releases of 5G based on the Release 15 standards, 5G handsets and devices will still exclusively employ 4G LTE positioning technologies. Today, there's already 75 commercial launches of 5G across 38 countries based on the Release 15 standards. Now, these mostly are small deployments in limited geographical areas, and 4G is by far the dominant underlay network. In the second phase, with the Release 16 standards, 5G new radio will then be used to enhance location methods, with location information exchanged between the user equipment and the base station natively over 5G. The R16 standards have just been frozen, and we expect to see the first network deployment and upgrades in 2021. And in the third phase, well, continuous enhancements to positioning will occur derived from the new 5G radio capabilities I discussed earlier on, such as the higher bandwidth, beamforming technologies, and network densification. One thing I think that is very clear is that 5G positioning needs accurate performance testing, and there are a number of key test challenges which need to be understood and addressed. Release 15 introduces some protocol changes to the current 4G LTE positioning capabilities. Now, this is to accommodate the new dual-mode 4G, 5G devices, and it's important to ensure that these changes do not affect performance. There's also the potential for new interference issues, introduced from the interaction between multiple frequency bands. For example, the 5G new radio in both the 3.5 and the 5 gigahertz range, combined with LTE band 4, will produce intermodulation distortion directly on top of the main GNSS band. Other common band combinations will have similar issues which need to be understood and tested. Latency must also be tested and measured for 5G to 4G fallback scenarios, such as when the 5G non-standalone device makes a voice call and then falls back from the 5G radio network to the 4G network. Here we need to ensure that the device successfully and rapidly enables 4G positioning. Processor lag on the device is also something that needs to be tested to assure that priorities are properly managed. As devices switch between modes, establish sessions, or manage background 5G data, they need to maintain positioning algorithms as a priority, especially during emergency call scenarios. And today's regulatory requirements are far more stringent than they were during the last generational switch, now requiring both conducted and over-the-air conformance testing to be done for emergency calling. And then you have sensor fusion. As I mentioned previously, no single technology is capable to meet all the positioning use cases. This means hybrid positioning schemes and sensor fusion are needed, creating the need to simulate and test multiple complex scenarios and combinations. You see, overall, location technologies will need to be adapted to handle more and more complex over-the-air test cases with array antennas and horizontal and vertical beams. Head, hand, and other obstructions will need to be considered for millimeter wave frequency devices. And indoor testing will become a critical part of location testing. Test methodologies that can span 5G and sensor fusion combined with lab and field testing, we believe will have the best chances for success. So now let's hand over to my colleague Roman for a poll And then Ivana from Fraunhofer will be exploring in more depth the simulation of 5G and GNSS signals for hybrid positioning.
Thanks, Steve. We will now jump into the poll. We will revisit the results of this poll at the end of the webinar. There are 2 questions and all results are anonymous. Question 1, what are the most important positioning sources for your use cases? For this question, you may select multiple answers. Question 2, what level of accuracy do you require for your use cases? It looks like most of you have completed the poll, so thank you for taking part. Please note, if you are watching this webinar on demand, that your response to the poll will not be counted. I now hand over to Ivana from Fraunhofer, who will talk about 5G and GNSS hybrid positioning simulation.
Thanks, Romain. I'll continue now with the development on the simulation environment of 5G and GNSS signals for hybrid positioning within the 5G Bavaria project at Fraunhofer IIS. Ray tracing is a powerful channel model that can be used to simulate the signal transmission, taking into account the surrounding buildings and objects. Here, in this special case, we see the line-of-sight components as white lines, diffractions and reflections due to the presence of 2 buildings as blue and red lines, respectively. All those components result in a distorted signal having influence on the time difference of arrival measurements and finally the position accuracy. Keeping this in mind, I'll start with our motivation. Present simulation environment going through overall architecture, different scenarios and transmitter types, and give 2 possible application examples. The conclusion sums up the most important insights, and the outlook gives the overview of our next steps. The location-based service comprises of a user equipment, satellites transmitting GNSS signal, and reference sources, or better said, different transmission and reception points of 4G and 5G signal, and a location server that distributes assistance data to the user equipment and receives measurements and location. The location-based services are used in industrial environment and urban area where we face the challenge to simulate the 5G signal for positioning purposes that includes the spatial consistency, and have a need to analyze a signal distortions. The simulation enables early tests and evaluations of campus network deployments. The basic part of simulation environment is SA Workbench, developed by Octal SE, that comprises of SEFFT, a 3D geometric data converter from and to the SDM format that is compatible to SA Workbench, of SE Adjatim Lite, a simple terrain generation tool that can be used to create geotypical scenes, and of SE Nav, a ray tracing channel model that includes different 3D scenes and different transmitter types. SENav has a special property, that is, its interface to Spirent SIMGen, GNSS signal generator from Spirent, in this constellation also known as SIM3D. SIM3D can be connected to the commercial GNSS receivers like Septentrio. SE Workbench was extended at Fraunhofer IIS with additional scenarios and transmitter properties. On the other side, SE Workbench can also be used standalone. In that case, we have SENav that outputs different simulation-related data per channel, multi-path link budget data, receiver and transmitter data are of a special interest for us. This data is used together with different signal generators, like the signal generator for 4G and 5G positioning reference signal, 5G sounding reference signal, or different types of GNSS signal, to generate raw signal and compute, for instance, time difference of arrival measurements. This is the part of the ranging package. Additional sensors package comprises of different sensors like barometer, IMU, odometer with their respective outputs. This package can either be combined or replaced by SIM inertial from Spirent. The output data from SENav extension are input for evaluation environment, specifically for position fusion and multipath detection and mitigation algorithms. The chosen scenarios and corresponding scenes enable the usage of real GNSS data. That's why we modeled the urban environment for specific Nuremberg area that enables the simulation and evaluation of urban micro and macro deployments, where the intersite distance is 200 and 500 meters, respectively. Additionally, we have to note that the current base station deployment can be included for comparison. Another chosen scenario is Fraunhofer IIS building in Nuremberg, enabling simulation for industrial environments and outdoor-indoor transitions and vice versa. Here, different outdoor and indoor deployments of transmission and reception points can be included. There is also the possibility to compare variable transmitter settings, like, for example, different carrier frequencies corresponding to FR1 and FR2 frequency ranges. For each scenario, different transmitters can be defined. SENav enables 3 different transmitter types. Satellites are one of them, and they can be used to transmit GNSS signal. In the case that SENav is used standalone, the post-processing based on snapshot data is done. Nevertheless, there are 2 other possibilities to get the GNSS measurements and raw data. That's either by using real or simulated GNSS data received by commercial receiver like Septentrio. In this context, the data is simulated by SIM3D, the SIMGen interfacing with SENav. Instead of Septentrio, different data grabbers can be used to record the raw data measurements and analyze them in a software-defined radio. Other transmitter types are beacons and jammers, whereas beacons are used as static transmitters and jammers as the transmitters following a signed trajectory. In that context, beacons can be used to simulate 4G and 5G positioning reference signals and ultra-wideband signal, whereas jammer can be used to simulate 5G sounding reference signal. Beacons have different properties that have to be defined. The most important ones to mention are carrier frequency, signal transmit power, and transmitter's antenna pattern. Finally, we come to different applications where presented simulation environment is used. Multipath is one of the biggest challenges for GNSS signals, especially in urban environments, where lots of reflections and diffractions occur. Here, SNAV is used to simulate and analyze the multipath on GNSS signal. Specifically, multipath link budget data is used since it contains all necessary information to label the simulated data. So we have three classes: the line of sight only, multipath without line of sight component, and multipath with line of sight component. For the multipath detection, the support vector machine with RBF kernel is used, showing the best performance among all other machine learning classification algorithms. Data used here is simulated using only SNAV standalone and additionally specific antenna model with two outputs. One output seen as right-hand circularly polarized antenna and other output seen as left-hand circularly polarized antenna. In the means of simulation, we have to note that we had to run the simulation twice with two different antenna types. In general, the specific property of GNSS signal is taken into account. In other words, we know that the transmitted GNSS signal is right-hand circularly polarized. When the signal reflects from an object, its polarization is changed from right-hand into left-hand circularly polarized. In this case, the GPS L1CA signal is used with 100 millisecond integration time. The results in the confusion matrix show a good detection rate. The second application is connected to the position fusion of 5G and GNSS signal measurements. For 5G, the sounding reference signal with 100 MHz bandwidth and at carrier frequency of 4 GHz is used, and in the case of GNSS, the GPS L1CA and Galileo E1BC measurements were extracted. The base station deployment contains of 6 transmission and reception points, with one of them experiencing always the absence of line-of-sight component. The GPS L1CA and Galileo E1BC measurements were extracted from septentrial logging based on real measurements taken at facilities of Fraunhofer IIS in Nuremberg, using Leica infrared light-based system as a reference system. The data from Leica were utilized to generate the trajectory for SNAV. Thanks to that, the simulated 5G data were synchronized to the real GNSS data. On the left picture, we see the positioning results. In blue, the 5G positioning, in green, the GNSS positioning, and in red, hybrid, in other words, 5G plus GNSS positioning. Note that the hybrid positioning results match best to the yellow curve being the reference trajectory. Looking at empirical cumulative distribution functions for 5G, GNSS, and hybrid positioning results, in other words, its horizontal error, we make following observations. Hybrid positioning outperforms the GNSS and 5G positioning, as we see in 98% of the cases we have horizontal error smaller than 4 meters. The 5G results show one of the major problems for the 5G positioning, the absence of line-of-sight component. Note just that in 30% of the cases, the 5G positioning result outperform both the hybrid and the GNSS positioning result, and look really great. The GNSS signal is distorted due to multipath, which is also visible in the results. We note that there are 98% of the cases where the horizontal error is smaller than 6.5 meters. Second position fusion application is a scenario with outdoor to indoor to outdoor transition. For that purpose, additional 6 transmission and reception points were placed indoor. Note that the GNSS signal can't be received indoor, and in this particular case, just a small number of satellites is visible when entering the building. Here we also used Leica as a reference system for trajectory generation that assures the synchronization between simulated 5G and real GNSS data. The real GNSS measurements on GPS L1CA and Galileo E1BC were extracted from the Septentrio receiver. Simulated 5G signal is 5G sounding reference signal with 100 MHz bandwidth at carrier frequency of 4 GHz. As in the previous scenario, the blue shows the 5G, green GNSS, and red hybrid positioning results. We note that the positioning results give the best match with yellow curve being the reference trajectory. Here it would be interesting to see what happens if smaller number of transmission points is used, or what is the outcome if we change the deployment of the base station. Since this is the simulation environment, it can be easily done. As in the previous position fusion case, we take a look at the cumulative distribution functions and make following observations. The 5G positioning outperforms both the hybrid and GNSS positioning due to the dense placement of the base stations and the transition to the indoor area where GNSS is either not present or very weak. In comparison, GNSS positioning performs worst due to severe multipath. GNSS multipath, on other side, has an influence on hybrid positioning solution. So we have to note that there is the need for GNSS multipath detection and mitigation methods to overcome the problems that we face in the hybrid positioning solution. To conclude, the SNAV with the software extension developed by Fraunhofer IIS can be used to simulate different kinds of ranging signals, GNSS and 5G, that enable the spatially consistent and realistic simulation due to the usage of the ray tracing, detailed analysis of signal distortion, since we have a lot of output data that can be used, and the position fusion of different ranging signals. The simulated data can be used with real data if certain highly accurate reference systems like Leica are used, which is especially useful for GNSS signals. SNAV and the software extension developed by Fraunhofer IIS can be used in combination with Spirent, so-called the Sim3D, that enables the wide variety of simulation possibilities. The next steps are the implementation of additional sensors package that has not yet been integrated in the simulation environment, the evaluation of machine learning procedure for multipod detection to see whether it correlates with the real measured data. If it correlates, this is a great news, since then we can use the simulation architecture and the complete simulation environment to train the specific machine learning algorithms that are useful for all kinds of applications. General goal is realistic simulation environment for different signals, enabling evaluations for various applications. Planned Spirent upgrade for Fraunhofer IIS should enable additional simulation possibilities with SNAV. Additional analysis of GNSS data and the distortion due to multipod. The use of carrier phase-based positioning methods enabling better position accuracy. And additional possibilities for position fusion with different ranging signals while using only the simulated GNSS data. Until the end of the month, there will be a video uploaded with hybrid positioning demonstrator that may give you additional impression on the overall architecture. If you want to be informed about it, you can contact us and we will give you the necessary information when it's so far. Thanks a lot for your time.
Right. Thank you, Ivana and Steve. So we will now look at the poll results, which Steve will talk us through.
Thanks, Roman, and I hope everybody enjoyed the first section here of the presentation. We'll get on to the Q&As in a minute. So let's just look at the results of the poll. I think the first question, I just remind everybody what you're asked. What are the most important positioning sources for your use cases? And obviously you could select as many as relevant. I think no real big surprises that GNSS and correction services are still the top two. I think they are currently still the dominant focus point for many applications today in terms of location and positioning accuracy. It's interesting to see the percentage there though for 4G, 5G becoming more and more important to start using assisted technologies to enhance that. I'm also really interested to see that just slightly further down the other sensors, LiDAR camera. I think if we'd done this poll a few years ago, that would have been a very small number. I think it's pretty interesting to see that percentage has grown as we look to, as I said, really exploit things like sensor fusion, where we can use more terrestrial based techniques to complement the non-terrestrial techniques and provide a greater degree of accuracy and actually leverage many of the capabilities that are now being built into both commercial and non-commercial systems and solutions. So I think it's a pretty interesting feedback. No big surprises at the top, but definitely some movements on the other technologies, leading towards that sort of sensor and hybrid positioning view. So let's look at the next poll question. Levels of accuracy that you'd expect or you'd require for your use cases. Again, actually very interesting. Obviously, a lot of the technology, especially GNSS, is focusing more on the meter level accuracy, as I mentioned at the start. The FCC, new requirements coming out for emergency services to let the meter levels. And there's no surprise that that's the dominant, but not by much. And I think it's really interesting to see centimeter level has really becoming quite an area of interest for the use cases that are out there today. And again, I don't think that's a massive surprise with what we're seeing in terms of the new types of applications that are being focused on. Where very precise accuracy is required, both indoor and outdoor. Whether that's in various industrial sectors, whether it's in automotive, whether it's even in the consumer and personal wearable sectors as well. So again, and that leads well back to the first answer. I think people were looking towards corrective measurements to provide that additional levels of accuracy to potentially get down to the centimeter level of accuracy. So I think that's a trend that has started, and we're seeing more of that. And obviously, we expect to see that continue as more and more, specifically mission-critical applications, are really looking for that more refined accuracy and robustness of accuracy, I should say, as well. Okay, so maybe we should hopefully have about 15 minutes left. We can jump into the Q&A.
Yeah, thanks, Steve, for taking us through the results of the poll. We can move on to the Q&A. So there is still a bit of time to submit your questions. For that, you can use the Q&A button at the bottom of your screen. And we already have lots of great questions, and we will try to answer as many as possible. So if we take the first one, so can I get 5G? And what will be the first applications using 5G positioning? I think that might be one for Steve.
Yeah, Roman, I'll take that one. So can I get 5G? And obviously, what will be the first applications using it? 5G today, if you look at, I think I mentioned at the start, there is about 75 plus now commercial deployments of 5G worldwide. In roughly about, I can't remember exactly, but I think it's about 35 or 36 countries have started deploying it. It's still rather limited, to be fair. Most of those deployments are in limited geographies, so they're maybe in some inner cities or some geofenced areas. There's very limited national 5G coverage yet, outside potentially, say, Korea. We're expecting to see more coverage capabilities come on over the next sort of 12 months with 5G in different regional markets. In terms of the first applications using 5G positioning, what I would say is, and I mentioned this at the start, in reality, in this first phase of 5G, which is primarily called non-standalone, which is really the 5G new radio interoperating with the 4G network, so anchored to the 4G radio and using the 4G core. In this first incarnation, the location services are still primarily using the 4G technology, so it's not really exploiting any of the new 5G capabilities yet. We'll expect to see the release 16, as I mentioned, is the next 3GPP standards for 5G, which has just been frozen, and that will be upgraded in some of these networks probably in the next sort of 6+ months. And then we'll start seeing the applications that will still start to exploit some of those 5G capabilities as part of that evolution. So, the types of applications that we're expecting to see, it's obviously still early days, But many of them to date have been focusing on things like industrial IoT and smart factories, where there's been a number of research projects going on over the last 6 to 12 months, with trying to focus in on getting down to centimeter level precise positioning indoor for those environments, whether it be for controlling autonomous vehicles or some of the robotic and precision engineering types of capabilities. In fact, there was a really interesting demonstrator that was done by Qualcomm recently, where they were doing a live over-the-air demo in a factory with multiple indoor small cells, actually demonstrating sub-meter 3D positioning. So we do expect the industrial space to be probably one of the potential earlier adopters of using 5G within a hybrid positioning scheme.
Right, thanks, Steve. So I think we can move to the next one, which is pretty much on the same line of the first question. So when can we expect to see the first 5G smartphones on the market?
Yeah, I mean, sort of quite aligned to that first answer. So obviously, there is actually commercially available today, well over 100 devices on the market. Now that's ranging from smartphones to 5G-enabled televisions right through to customer prem equipment. What I would say that those first incarnations, though, are primarily based on supporting the non-standalone architectures of 5G, and the first release 15 version, which is from a device perspective, is still requiring the devices to use LTE as the cellular assisted capability for location. But there are a number of major chipset and device manufacturers, as I said, about on the market today. Qualcomm's with its Snapdragon 865 ranges, Huawei, the current 990 processors, and Samsung. I think the Exynos 990s are, they're all out there on the market at the moment. We would expect to see the first wave of release 16 devices coming in 2021. Now that the standard has been frozen. And as I said, and these will be the first ranges that will really exploit that duality of current techniques, but also really the exploiting the 5G capability. But there are 5G devices available today, but as I said, the reality is they're still location and positioning is still fundamentally based on 4G within them.
Thanks, Steve. Yep. And we can move on to the next question. So is SCNAV extend available open source for testing on or research purpose? This one is maybe more for Ivana.
SNAV extension is currently not available open source since it is still under development. When it will be so far, at least part of it will be available for sure. And in that case, you also need some example data from specific SNAV scenarios that will then also be at your disposal for analysis and testing purposes.
What sort of 5G jamming signal did you simulate? Were they static or moving? I think that's again a question on Ivana's presentation.
Yes, for sure. So in general, the jamming signals are the moving signals. So since the transmission points are static that we use, only beacons were used for the simulation purposes. Nevertheless, one could use the jamming signal to simulate the transmission between, for example, two moving UEs.
Thanks, Ivana. Thank you. Yes, so I think this will be our final question. We had a lot of other questions today, and we won't be able to reply to all of them, but we will try our best to get back to everyone who submitted personally after the webinar. So the last one is again for Ivana, and it's how many GNSS multipath signal did you simulate per line of sight signal?
So since for the simulation of GNSS multipath, we used the SNF standalone, there are two settings that can be configured there. So in general, one configures the number of reflections and enables or disables the diffractions. And in our case, the number of reflections was set to 6, what is the maximum, and the diffractions were enabled. So we had approximately 5 to 15 non-line of sight components per satellite.
Okay. Thanks, Ivana, for this answer. So I'd like to thank you, the audience, for attending this webinar and also submitting all your questions. And I also like to thank Ivana and Steve for participating today. One final note, so this webinar has been recorded. You will receive an email with a link to the recording in early August. Thanks again for joining, and we look forward to seeing you at future events.